Now let's let A be the matrix 1, 2, 3, negative 1, so that a vector xy is transformed by the matrix A to the product A times xy, which is the 1, 2, 3, negative 1 multiplied by xy. Now, this is called the matrix with respect to the standard basis. And I'm not going to belabor exactly why that is. Let's understand the matrix with respect to a different basis so we have a better understanding of what it means for this to be the matrix with respect to the standard basis. But all this means is that xy are the real numbers that represent a vector, and A multiplied by xy gives you the real numbers. In this case, it would be what? X plus 2y, 3x minus y. So I could actually write that out. So let's write that out. That's x plus 2y, 3x minus y. Okay. This matrix represents then the transformation T of xy equals x plus 2y, 3x minus y. Now, we can express xy in terms of some other basis, in particular the basis 1, 2, 1, 1, relating to this basis, okay? So, in terms of this basis, xy will be this inverse matrix multiplied by xy. That'll be your C1, C2, that'll be the representation of the xy vector in the new basis. So, xy, using this matrix, gives us C1, C2, and that C1, C2 represents our same vector, but relative to the basis that we have here. Now there's some matrix then that we can multiply by C1, C2 that gives us the representation of the transformed vector, the representation of this vector, but with respect to this basis. Okay? And that's going to be obtained by A prime times C1, C2, whatever that comes out to be. We don't know what A prime is yet, but we'll be able to find it. Okay? Then we can transform from this basis down to our standard basis. Now what matrix takes us from the standard basis to the basis B? It's the inverse of the 1, 2, 1, 1 vector. Okay? And what matrix brings us from here down to here? It is the 1, 2, 1, 1 vector, the vector whose columns are the eigenvectors. And we can see that related here, that if C1 and C2 are the components up here, then multiplying by this matrix gives us the xy, because this just means, I don't want to digress that far, it'd be confusing, so we'll keep it there. Just in this context we can see what this means, and we'll be seeing it again. We'll explain it repeatedly as we go. Essentially, whatever the two components are here, you multiply the first number by your first eigenvector, second number by your second eigenvector, and add what you get, and you get the representation down here. Okay, well, this is a matrix that we'll call P, and this is a matrix that we'll call P inverse. Okay, so that if we now want to find this matrix, okay, we start with a vector represented here, and we use the P matrix to bring it down to the standard basis, multiplied by our A matrix, and then bring it back up to our B basis using the P inverse, the inverse of this matrix. Okay, so if we want to go this way, if we want to take a vector down here and lift it up to this basis, we're going to use the P inverse matrix. If we want to go from here down to here, we're going to use the P matrix. Now, if we wanted to be here and come up to here, we're going to have to do the reverse and use the P inverse matrix. That's how we go up. And then going down from here, we would use the P matrix. So the P matrix takes us from the B basis to the standard basis. There it is, just the columns consisting of the basis vectors. And the P inverse matrix takes us from the standard basis up to the B basis. Okay, make sure you see that whole idea. I can see a carelessly written word here. I want to fix that. This transforms a vector in the standard basis, not a vector is the standard basis, to the basis B. Okay, so to go from the standard basis up to the basis B, we use the inverse of this vector whose columns are the basis vectors, and so forth. And here we just explain what we've already said, that the P matrix then transforms from the basis B to the standard basis. And that's what we have here. So, what do we end up with? The matrix A multiplied by xy is equal to what? Well, if we start with the vector xy and go directly across here, well, of course, we get A times xy. Another path is we start with a vector here, we transform it up to this basis, up to the B basis, then we apply the A prime transformation, the A prime vector, and we get the transformed vector according to this basis, and then we transform back to the standard basis. Now how do we do that? We start with xy to go up here, we apply P inverse. So the first thing that happens to xy is P inverse. Well, here's xy. First thing that happens to xy is P inverse. Okay, then we have the matrix A prime, and then we bring it back down here using the matrix P. So this equation just says what the picture says. If we go from here to here, it's just A times xy. If we go here up to here, it's P inverse times xy. Here we've got it. To which we apply the matrix A prime, multiply the matrix A prime by P inverse xy. And then we apply the matrix P to express that in terms of the standard basis. This has to equal this. Now, if this equals this, then we can write that a little more simply. Just take the vector xy out of it. The matrix A has to equal the matrix P A prime P inverse, and that's the relationship between the matrix A and the matrix A prime in terms of the matrix P consisting of the column vectors. Okay? The matrix A prime, well, we can solve this for A prime. Multiply on the right, both sides on the right, by P, and we get rid of the P inverse. We get AP equals P A prime, and then multiply by P inverse on the left. It takes care of this P, and we end up with A prime equal to P inverse AP. Now, A prime represents the same transformation as A. It's just that A prime is the transformation as it appears in the basis B. A is the matrix as it appears in the standard basis. Same transformation, but we need a different matrix in a different, if we express our vectors relative to different bases.